C13 NMR is a little bit simpler because we don't have coupling, and it's a little bit easier to interpret because there's fewer numbers of carbons most of the time than there are hydrogens. One thing that we do in a C13 NMR is that we decouple any protons from the carbon-13, because the protons actually could split the carbon-13 and really make a complicated spectrum, and the peaks are kind of faint anyhow because there's not that much carbon-13, and splitting them out would make them even fainter. So we do something called decoupling by causing the protons to constantly flip back and forth, and averages out the signal, so you only get one signal and no splitting. We don't have carbon-13 split each other because rarely do you have a carbon-13 next to a carbon-13 in a molecule because there's such a low percentage of it. So that simplifies the whole spectroscopy of carbon-13. This is a typical spectrum for carbon-13. 0 is where TMS would be. And we can see protons all the way down to about 220 parts per million. The alkyl groups are going to be in the upfield range, just as we have that in proton NMR, except here the range is from 0 to 55. The acetylenic carbons are going to be at upfield compared to vinyl and aromatic also, because of the way that the electrons circulate. They have the same impact on the carbon than as compared to the vinyl and the aromatic. So these carbons are at these parts per million. Here I'd say about 70. Here this is about 120 average, 140 average. For nitrile, the carbon in a nitrile would be about 120 average. And then we have the carbonyl, and that's way downfield, 1600 to 220. So it's kind of off in this region by itself and easy to recognize a peak there. The chemical shift is also influenced by whether it's primary, secondary, tertiary, or quaternary. Because carbons are more electronegative, the more carbons you have attached, the farther downfield it will be. So quaternary really are the farthest downfield. You can recognize a quaternary also because the peak is really small compared to the others, because for something I'm not going to go into, the abundance of finding C13 in a quaternary carbon is kind of low, and so we tend to have really small peaks for quaternary carbons, but they also tend to be on the downfield range of the alkyl group. Then tertiary, then secondary, and then primary are always going to be farthest upfield. Because identical carbons have the same peak, what we find out, major thing that we find out from carbon-13 is the number of different carbons. So when comparing a spectrum to a structure, you find the equivalent carbons and don't count them twice. Two that are identical you have to count as one. It's because the symmetry eliminates some of those peaks. The carbons are identical to each other due to symmetry. And then I already told you that carbons without hydrogens will have smaller peaks. Carbons without hydrogens tend to have less opportunity to be carbon-13. Here is a carbon-13 spectrum. Here is our TMS at 0. Notice my primary carbon is all the way downfield. It's also farthest from the chlorine. All the way, upfield, almost at 10. Then we have the next in line, then the next in line, then D, then E, then F. Our solvent here is deuterated chloroform, and you see this is the peak due to it. You see that a lot in there. It's one of the most common solvents. And so when you see this little peak, is really a triplet, 3 even same peaks. At about 78, you just ignore it. So we have 6 different carbons here, and we see 6 different peaks. There's something called DEP carbon-13, and you actually, I'm not going to go into how it works, but you get separate spectra for how many hydrogens are attached. In the DEP spectra, you do not get a spectrum for the quaternary carbons, they're gone. And for each set type of carbon, you get a spectrum. So this is what we get from the DEP spectrum. One spectrum for the carbons that have 3 hydrogens attached, one for the ones that have 2 hydrogens attached, and one spectrum for the ones that have 1 hydrogen attached. If I go up here and I look at all the carbons, there are actually 1, 2, 3 quaternary carbons, carbons that have no hydrogens attached. Those carbons are the smallest peaks here. Okay, the others all have hydrogens attached. If I look and see how many carbons I have, this methyl is different from this methyl because this one's close to the carbonyl, this one's over this side. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different carbons. So what we see here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different carbons in the spectrum. In MRI, we're doing an NMR of the protons in your body. So if you look at an MRI, they are looking at the signals of common protons at particular signals, and they map them using a computer and map where are the different protons. They can create a picture that shows anomalies of, let's say, the inside of someone's brain or their spinal cord. It's all using NMR technology. So here are some you try it. So let's look at these. Which of the following nuclei will you not be able to do nuclear magnetic resonance on? Well, we've been talking about that you have to have spin, and to have spin, you need to have an odd mass. And if you look at this, this has an odd mass, this has an odd mass, and this has an odd mass. So all of those are going to have spin. But the carbon-12 has an even mass, and so they have no magnetic spin, and they will be invisible in any NMR. So which of the following is true for C13 NMR? Well, let's go through these. The number of carbon atoms in the molecule can be determined. Well, that's not really quite true because we can only determine the number of different types of carbon atoms. The number of hydrogen atoms in the molecule can be determined. Well, we can determine how many hydrogens are on a particular carbon, but we don't know the total number of hydrogens. And so that means this number 4 is wrong too. What can we deduce? Well, we can feel pretty confident that there are certain functional groups in the molecule based on the location of the peaks. Chemically equivalent nuclei always show a single absorption. Is this true or false? That is true. How many signals or peaks do we see in a C13 NMR of this molecule? Well, if I go and I look at this molecule, you'll see it's symmetrical. I can draw a plane going down through this molecule, and so this side of the molecule is the same as this side of the molecule. So there are 1, 2, 3, 4, 5 different carbons. How many C13 peaks will you see in a spectrum of this compound? Well, let's count the different hydrogens, carbons. This carbon is different from, is the same as this one, which is different from this one. So this would be 1 for those two, 2, 3, 4, 5, 6 for that one. 6 different carbons. Which of the following molecules best fit this peaks found at these part per millions? Well, if I look at these peaks, I see there are 5 different carbons. So the first thing I do is I look for a molecule that has 5 different carbons. So let's count them here. 1, 2, these are different from each other, so 3, 4, 5, 6, and that methyl is different from this one, so it's 7. That won't fit. Okay, let's look at this. This is different from that, and this is different from that because this side is closer to the hydroxyl. So count them, 1, 2, 3, 4, 5, 6, 7, 8 peaks. Well, let's go and look at this. This is different from this. And of course, this is different from that, and this is different from that. So again, 1, 2, 3, 4, 5, 6, 7, 8 peaks. But if I look at this one, I can see there's a plane of symmetry going down through the middle of this compound. So this methyl is the same as this methyl. That carbon's the same as this one. That carbon's the same as this one. And then this and this are different from each other. So 1, 2, 3, 4, 5 peaks. And there are 5 up here. Choose a relationship between HA and HB. Well, chemically, they're related because they're both alpha to a carbon holding a chlorine. But this one is on top of the ring and this one's below. What you always do is you replace and put a deuterium here and then put a deuterium here. And you can see that the deuterium would be trans to the chlorine and this deuterium would be cis to the chlorine. Those are diastereomers. And so what are they? Diastereotopic. Figure out what the relation is between HA and HB. If I look at this compound, you can see that if I put a deuterium here and then another time put a deuterium here, this carbon's going to still be achiral. So they are chemically related because they're identically attached. They're not diastereotopic because you don't make diastereotopes. They are not enantiotopic because you don't make enantiomers. I should have said diastereomers, sorry. So what are they? They are homotopic because they are identical. When you replace each of these with deuterium, you end up with identical compounds. So they are homotopic. Okay, order these from the lowest chemical shift to the highest chemical shift. That means from the lowest parts per million to the highest parts per million. So you're going from the upfield to the downfield value. All right, the farthest downfield would be the aromatic hydrogen, then the vinyl, and then alpha to the carbonyl, and then an alkyl hydrogen. So HC is going to be the lowest chemical shift value. So it's going to be one of these. Then it's going to be the hydrogen alpha to the carbonyl, so HA, so one of these two. Then what do you have to know? This is more upfield than the aromatic. This is going to be around 5.5. This is at around 7. So the order that is correct would be 3. Will proton NMR allow you to distinguish between the following two molecules? No. These are enantiomers, and enantiomers cannot be distinguished in NMR unless you put them in a chiral solvent, and that's really unusual. So their spectra would be identical. Demerol has this structure. How many peaks would you expect to see in a C13 NMR? There's a lot of carbons here. Let's go ahead and look. 1, 2, 3, 4. This is symmetrical, so 5, 6, 7. This is symmetrical, so 8, 9, 10, 11. You would expect to see 11 peaks. Could this spectrum be for this compound? It can. Let's go see and see how. Let's start down here at 1.4. That would be these two methyl groups. Because those methyls are on different sides of the double bond, they're different. So you see two separate peaks for them. There are no hydrogens here, so they're singlets. There's one hydrogen right here. Where would that be? Well, remember we said that hydrogens on a double bond would be about 5.5. But we see there's a hydroxyl group nearby. That's shifting it a little bit. So that's shifting it down this way. This hydrogen has two neighbors here. So this actually could be a triplet for due to those two hydrogens. It's kind of a messy triplet, but this is a noisy spectrum. Then if we look at the two hydrogens here, they're going to be farther upfield, but they're going to be split into a doublet because there's one hydrogen here. So something with an integration of two, like this, could be a doublet, yes. And what is this last peak right here? Well, that's probably your proton. Because this is such a noisy, faint spectrum, you can't really see how broad that peak is. And that sometimes does happen with hydroxyl groups. So they're not always amazingly broad like we saw with the ethanol spectrum. But you can test by shaking this with deuterium oxide, and what would you find? You would find that peak would disappear. So this can be that compound. Which compound best fits this NMR? First, let's go through the integration. This looks like it's more than this. And this looks like it could be two methyls. If that's 6, this would be 5. If this is 5, that means the benzene ring is probably monosubstituted. And then look at this. This is a septet. A septet that looks like it has an integration of about 1 compared with 6. That's a pattern that's indicative of an isopropyl group. This was a pretty hard spectrum for you to do as a first try in interpreting spectra. But what does this point to? This points to monosubstitution, and it points to an isopropyl group. So this is the correct compound. Okay, can this molecule, which one of these molecules would fit this spectrum? Well, the first thing that we're going to do is we're going to look at the spectrum and look at where the peaks are. At 0, this must be a TMS peak, so it does not fit. Why did someone integrate it? That was silly. You never integrate a TMS peak, but that's what's always at 0. Then let's look and see how many other peaks we have here. We've got one here that's a quartet, one here that's a singlet, one here that's a singlet, and one here that looks like a doublet. That's 4 different sets of hydrogens, and we know this is hydrogen because the part per million scale is 0 to 10. If I look down at these molecules, first thing I need to do is look and see how many different hydrogens are on these molecules. 1, 2, 3. This does not fit. There's only 3 sets of hydrogens. Here I have 1, 2, 3, 4. Well, that could fit up here. There's 4 peaks. Let's look at this. 1, 2, 3, 4, 5. That won't fit 5 sets of hydrogens. 1, 2, 3, 4, 5 sets of hydrogens doesn't fit. 1, 2, 3, 4, that could fit. So it's between these two. Now let's look and see if we can get the functional group, the protons on the functional groups figured out. Right here we have a vinylic hydrogen. Okay, that vinylic hydrogen runs from, let's say, 4.5 up to 6. It ought to be on the higher end because there's an oxygen attached to the double bond. Let's look up here. We're at 5 with this one. Could it be? Possibly. Let's look at the splitting. You see it's a quartet. What would this hydrogen be? Well, there's 2 hydrogens over here, so this should be a triplet. So it can't be this quartet. Let's look over at this molecule. Let's look at, well, we've got an acetylenic proton right there, and it would be a singlet because there's no hydrogens here. And where do they show up? Well, they show up in the range like 2.5 or so, maybe. Let's look up here. There's one at about 2.9. Well, that's a reasonable range for this proton. Let's look at this methyl group. This methyl group is going to be a singlet. Where are we going to find it? Well, that methyl group, I'm going to say, is going to be like 2.5 or so. Well, there's one here at 3. With that acetylenic group nearby, that could be it. And it does show it to be a singlet. So this could be the singlet for the acetylenic proton. This could be the singlet for this methyl group. Well, let's look at the others. There's a hydrogen here. That one hydrogen is going to be split by 3, and that would make it a quartet. Now, it's adjacent to an oxygen, but it's also adjacent to an acetylene group. This could be that. What about these 3 hydrogens here? Those 3 hydrogens would be split by this one. Well, that is a doublet, and it could very well be this methyl group. So if I'm going to pick a structure that fits, it's going to be that one. Which one of these molecules will fit this spectrum? Well, there's only one peak in the spectrum at 4.4, and it's a singlet. So all the hydrogens are going to have to be the same. And if I look at this spectrum, I see hydrogens here, and a hydrogen here, and a hydrogen on the hydroxyl group, and even a hydrogen here. So no, it can't be this, and it can't be this. Hydrogens here, hydrogen there. It can't be that. Same thing here, too many different types of hydrogens. Whereas if I look at this, dioxane has 2 hydrogens here, 2 here, 2 here, and 2 there. They're all identical to each other. So what are you going to see? One peak, and that's it. Which molecule best fits this spectrum? Well, again, someone integrated the TMS, which you don't do. Let's look at the rest of the spectrum. If I look at this, first of all, notice this peak. It's kind of broad. What does that indicate? Well, that indicates to me a protic compound. So I'm going to say it's going to be one of these. Okay, next let's look at the splitting. I see here this is what looks like a septet, and this is a doublet. Whenever you see a septet and a doublet, that says isopropyl. So it's not going to be ethylamine, it's going to be one of these two. Which one could it possibly be? Look at the integration. See, this is about half of what this is. And this is going to be 6. So if this is 6 and this is 2, it's got to be this amino, isopropylamine group. There you go. Which one of these molecules fits this spectrum? Well, the integration here is given it to you in numbers, so that really helps. There's 9 and there are 3, and they're both singlets. What could that possibly be? Well, whenever I see an integration of 9, I think T-butyl. Whenever I see an integration of 3, I think methyl, because that's really common for those to make that. So if I look for anything that has a methyl and a T-butyl group, it would be this, and it would be this. This won't fit because there's only 2 here, and then you'd have a third peak for this. This won't fit because you'd have a peak for the hydroxyl, 2 here, and then 9 here. And this would give you 6, and then 1 for this, and 1 for this, and 1 for this. 1, 2, 3, 4 peaks. That's not going to fit. So which one of these two will it be? Well, if I look at this methyl, it's farther downfield. Which would be farther downfield, attached to a carbonyl or attached to an oxygen? Well, attached to the carbonyl would actually be farther downfield, because not only do you have the oxygen being electron withdrawing, but you have the pi bond there. And the methyls in the T-butyl group are not directly attached to the oxygen, they're on the carbon that are attached to the oxygen. And so this is the structure that best fits.